Welcome back. Today we are mapping out the spaces between whole numbers to see exactly what fills the gaps. This diagram shows the number categories you know. We start with natural numbers, expand to whole numbers, and add negative values for integers. Zooming out, integers live inside rational numbers, while completely separated is the oval of irrational numbers. Knowing which zone a number belongs to matters because each category follows specific algebraic rules. Rationals have decimals that stop completely, like 3/5 becoming 0.6, or loop infinitely, like 1/3 repeating. Irrationals, like the square root of 3, continue without terminating or repeating. But watch out, because 7.478 repeats exactly, it remains rational. A decimal's visual sequence serves as proof of its identity. A predictable pattern means it is rational, while a sequence that never repeats or ends is irrational. Now let's look at roots. A surd is a specific type of irrational number, the root of a rational number that yields an irrational result. Not every number under a radical sign is a surd. The square root of 180 simplifies to 6 root 5. Since it remains non-repeating and infinite, it is a true surd. But the cube root of negative 125 resolves to exactly -5, which is an integer. These classifications can change during an operation. If we add 3 plus root 2 to 5 minus root 2, the positive and negative roots cancel out. We are left with 8. Two irrational expressions have combined to create a rational result. In other cases, irrationality spreads. If you multiply a rational 2 by an irrational root 3, the resulting 2 root 3 remains irrational. Whether a final result is rational or irrational depends on how the numbers interact within the specific operation. In algebra, we standardized fractions by removing irrational numbers from the denominator. This process, called rationalization, makes expressions easier to compare and simplify in larger equations. Take the fraction 1 over root 5 minus 2. To simplify this, we need to clear the root 5 from the bottom. We do this using the conjugate. By changing the subtraction in the denominator to addition, we create the term root 5 plus 2. When we multiply the original denominator by this conjugate, it follows the difference of squares identity. Root 5 squared is 5, and 2 squared is 4. 5 minus 4 leaves us with a rational denominator of 1. The conjugate uses the properties of squares to eliminate the root, resulting in a stable, rational denominator. Try this on your own. Pause the video and rationalize the denominator for 1 over root 2 plus 1. To clear this, multiply the top and bottom by root 2 minus 1. The bottom simplifies, leaving the final result, root 2 minus 1. To summarize, rational decimals terminate or repeat. Irrational decimals never repeat and never end. And to rationalize a denominator, use the conjugate to square away the root. Mastering these definitions and procedures lets you simplify complex expressions into their standard, readable forms.